All right, I'm going to go ahead and start us off here. Hi, everyone. Welcome to the National Operations Center of Excellence webinar, Road Weather Spotlight Series, California Wildfire Program, and National Weather Service Partnership. My name is Kyla Elzinga, and I'll help facilitate today's webinar. The National Operations Center of Excellence offers a variety of resources to support the transportation systems management and operations community. You can go to NOCoE's website at transportationops.org to browse through links for TSMO resources and news. Previous webinar recordings and case studies can be accessed from the NOCoE resources pages. A few logistics for today's webinar. First of all, we are recording this webinar and the recording will be available on the NOCoE website. All of the attendees are encouraged to stay engaged by using the Q&A feature for questions and the chat feature for comments. So these are both on the bottom or top of your screen, depending on your Zoom orientation. And we have a question and answer session at the end of the presentation. So if you have any questions, we encourage you to enter them into that Q&A area as they come to mind at any time. Also, please feel free to enter your name and agency in the chat to say hello to your peers. And now I'll hand it off to our moderator, Jeremy McGuffey with the Federal Highway Administration Office of Operations to get us started. Thanks, everyone.
Thank you so much, Kyla, and thanks to NOCoE for hosting these webinars. Hi, everyone. Welcome to another edition of the Road Weather Spotlight Series. Today, as Kyla mentioned, we'll be talking about the California Wildfire Program and National Weather Service Partnership. Just real quick before we move on, I just wanted to get you familiar, if you're not, with the Road Weather Management Program. Here at FHWA, the Road Weather Management Program is responsible for mitigating the impact of severe weather across the surface transportation network, ultimately improving safety and mobility. We do this through stakeholder engagement and outreach, road weather research and development, technology transfer and deployment support, and finally, training. So this Spotlight Series is an opportunity to highlight innovative and noteworthy practices in road weather management. Today, as I mentioned, we're going to be covering California's Wildfire Program and their partnership with the National Weather Service. Next slide. So just before we get started, though, I do have some disclaimers. These are on all of the FHWA presentations. It's just I'll actually read it off here. This presentation was created and is being co-presented by both the Federal Highway Administration and an outside entity. The views and opinions expressed in this presentation are the presenters and do not necessarily reflect those of FHWA or the U.S. Department of Transportation. The contents do not necessarily reflect the official policy of the U.S. DOT. The U.S. government does not endorse products or manufacturers. Trademarks or manufacturers' names appear in this presentation only because they are considered essential to the objective of the presentation. They are included for informational purposes only and are not intended to reflect a preference, approval, or endorsement of any one product or entity. Except for statutes and regulations cited, the contents of this presentation do not have the force and effect of law and are not meant to bind the states or the public in any way. The presentation is intended only to provide information. Looks like the bottom piece is cut off, but the information regarding thank you. We can just move to the next slide. All right. So as I mentioned, we have a pretty nice agenda today on California's Wildfire Program. We have three presenters: Dr. Tom Corringham with the University of California, San Diego, Robert Scott with California Office of Emergency Services, and then finally Eric Schoening with the National Weather Service. We will have the opportunity for Q&A, but I do encourage you at the bottom of the screen there to click the Q&A button to enter any questions that you may have so that those can get answered in real time. But after all three presenters, if there are any outstanding questions that anyone has, we'll have a few minutes set aside to do some Q&A. So with that, we'll move on to our first presenter, Dr. Tom Corringham. And while we're getting that set up, Dr. Tom Corringham is economist at the Center for Western Weather and Water Extremes at Scripps Institution of Oceanography, University of California, San Diego. His research focuses on the social and economic impacts of extreme weather events in sectors including transportation, agriculture, insurance, water management, and emergency management. Tom, I'll hand things over to you.
Great, thank you, Jeremy, and thanks to the NOCoE team for the invitation, and thanks to all of you here today for your time. My name is Tom Corringham. I'm an economist at the Center for Western Weather and Water Extremes here at Scripps Institution of Oceanography, University of California, San Diego. I know the major topic of today's webinar is wildfire. I'll be talking about atmospheric rivers, different topic, but related in several ways to wildfires. The main relationship being the compounding impacts of wildfire followed by storms produced by atmospheric rivers, leading to debris flows. I have actually done some other work on the impact of wildfire on collisions and road safety, but my talk today will be primarily focused on atmospheric rivers and impacts on road safety and mobility in the transportation sector. I would like to acknowledge our funders at the Aurora program based at Iowa State, especially Zach Hans and Neil Hawkins for their support throughout this project. Next slide, please. So just to give some background, atmospheric rivers are severe winter storms that affect the west coast of all major land masses at the mid-latitudes, including the west coast of the United States. Like other forms of inclement weather, atmospheric rivers decrease the safety of roadways, bringing rain, ice, snow, increasing collisions, delays in travel time, and reducing, in some cases, traffic flow. So the key question that we were seeking to answer in this study are, what are the impacts and costs of atmospheric rivers to the road transportation sector? Our focus was on passenger vehicles, not on the freight transport system. And also we asked how atmospheric river forecasts could be used to reduce these costs. Our objectives were to develop a methodology to estimate the costs of atmospheric rivers and apply this methodology to focus sites in California, Colorado, and Utah. Next slide, please. Here we have a video that will show about atmospheric rivers.
Imagine a river in the sky with more than twice the water of the Amazon. It's called an atmospheric river. Atmospheric rivers are long, narrow bands of concentrated water vapor that produce major amounts of rainfall. Atmospheric rivers begin in the warm waters of the Pacific, where water evaporates into the air. When this humid air meets a Pacific storm, the water vapor is concentrated and driven toward the coast, becoming a fire hose of rainfall and wind. Once the atmospheric river reaches the coastal mountains and the inland Sierra, the collision squeezes additional rain and snow from the system. Atmospheric rivers are responsible for up to half of California's annual precipitation. Scientists at Scripps Institution of Oceanography have developed a new system that rates atmospheric rivers on a scale from 1 to 5. The rating system helps identify atmospheric rivers that are beneficial, such as those that replenish reservoirs, and ones that produce hazards like flooding. Understanding atmospheric rivers is key to improving weather forecasts for better managing water resources and predicting flood risk.
Great, thanks for that. So just to give you the headline results here, we did find that atmospheric rivers reduce road safety and mobility at our 3 test sites. We found specifically that atmospheric rivers decreased demand for road travel on California's I-5 freeway, and atmospheric rivers increased crashes, road closures, and delays at focus sites in Colorado and Utah. We also find that forecasts could reduce costs to drivers and road management agencies. Specific results in California on the I-5, we found that passenger vehicle flow decreased by up to 17% during atmospheric river conditions at an estimated cost of $135 million per year. In Utah, we considered 4 test sites, and we focused only on accident costs, and there we found costs of $9,000 per freeway mile, or approximately $890,000 per year. And in Colorado, we looked at a single month, March 2019, and found that delays associated with atmospheric rivers cost over $2 million. Next slide, please. The data that we used were road safety and mobility data from state departments of transportation, including incident reports and traffic census data. On the atmospheric river side, we used catalogs of atmospheric rivers, their incidence, and their intensity. And I should just take a minute here to describe the atmospheric river data. So unlike hurricanes or tropical storms, it is not always obvious what counts as an atmospheric river. A strong one, you kind of know it when you see it, but the weaker ones are a little bit harder to distinguish from other inclement weather systems. So there are detection algorithms, and the one that we used is known as the Guanin-Walliser detection algorithm that comes out of NASA's JPL. And this is a relative scale as opposed to an absolute scale. So atmospheric rivers can be measured in terms of the amount of water vapor that travels over a given point in space, or it can be measured in terms of the relative amount of water vapor. And in this one, we use a relative scale, which allows us to capture weaker atmospheric rivers that occur to the east of the Sierra Nevadas, so including Colorado and Utah. So our numbers for Colorado and Utah are the atmospheric rivers that were captured there were somewhat weaker than the ARs that were captured in California. So just a note there. In terms of the impact analysis, we matched the Department of Transportation data to the atmospheric river data. And this methodology that we developed, I should note, could be applied to any form of inclement weather. So if you have Department of Transportation incident and traffic census data, it can be matched to weather data, and it's possible using our methods to back out costs of these different weather events on road transportation networks. We conducted a statistical analysis linking these data sets, controlling for day of the week, time of day, and location effects, and we estimated the impacts of atmospheric rivers over baseline conditions. For our economic analyses in Colorado and Utah, we used estimates of delay costs and accident costs from the literature, and using the impacts of the atmospheric rivers, we were able to estimate the costs of these impacts. In California, we developed a demand model for vehicle miles traveled to estimate the costs of decreased mobility. Next slide, please. For the Colorado focus site, we chose the I-70 west of Denver, and this was in consultation with Colorado DOT. This is the major east-west freeway in Colorado. West of Denver, it extends up into the Rocky Mountains near many of the major ski resorts. So it's a very busy corridor. We used road closure data, and the data we were using included the location of the closure, the direction, the date, start and end time, type of closure. We also had data on events and event type, subtype, and closure durations. And we, in the data, there were 434 events and 98 closures. So this was over a single month. And just to think of this, there can be closures at multiple sections on the freeway, eastbound and westbound. So that's why the number of closures is greater than the number of days in the data set. And of these 31 days that we considered, 10 of them were atmospheric river days. So about a third of the days were atmospheric river days. And I should just note that March 2019 was a very significant avalanche cycle in Colorado, which is why the Colorado DOT was interested in this specific month. Next slide, please. And here we just see the I-70 corridor of interest. Next slide, thank you. So here are the key results. The table on the left shows that closures increased significantly. So full closures, there were about 2.3 on non-AR days, and on AR days, there were over 20. So that was a 8 or 9-fold increase in road closures. Chain restrictions were also up, general events and severe incidents were up as well. So severe incidents increased by 61%, for example. On the right, you can see the traffic flow by time of day on atmospheric river days and non-AR days. So in black, you can see a non-AR day traffic flow over the course of 24 hours. And in the red line, you can see the impact of atmospheric rivers decreasing that traffic flow. In the lower panel, you can see that decrease in blue. We used estimates of the cost of delays to get the total cost of delays here was $2 million. So this is only considering delay costs, not considering the reduction in road mobility and not including the cost of increased accidents and incidents on the road. Next slide, please. For Utah, we chose 4 focus sites, again, in collaboration with the Utah Department of Transportation. If you're familiar, you would probably recognize these sites: the I-70 at Clear Creek Canyon, the I-80 at Parley's Canyon, US Route 6 from Spanish Fork to Helper, and US Route 91 from Brigham City to Wellsville. These are all mountain passes that are susceptible to extreme weather conditions, road closures, and accidents and other incidents. For this data set, we had 7 years of data. We considered October 2012 to December 2019. We stopped before COVID as everything changed rather dramatically during COVID. So we wanted to keep conditions fairly stable across the analysis, which is why we chose that 7-year period. The data included the location of the accident or collision, the direction, freeway direction, the date, the time of the incident type, and lane and road closure duration. Next slide, please. Key results. We found that there was an increase in accidents associated with atmospheric rivers, unsurprisingly, at these 4 sites. The increase ranged from 4% on the I-80 to 20% on US 91, and the cost associated with this, again, using costs from the literature of non-fatal collisions, was $9,000 per freeway mile, an additional $9,000 per freeway mile over normal conditions, or $890,000 per year. Next slide, please. For California, so for Colorado, we looked at delays. For Utah, we looked at collisions and accidents. And for California, we wanted to look at road mobility, so actual impact of atmospheric rivers on passenger vehicle flow and vehicle miles traveled. On the left, you can see the freeway system in California, and on the right, you can see the I-5, which extends about 800 miles from the border of Mexico up to the border of Oregon. We divided it into 4 sections: Southern California, which the I-5 passes through San Diego and Los Angeles, so very busy stretch of the I-5, through Central California, which is more agricultural and less busy section, near the Bay Area, east of the Bay Area, and then Northern California, which is higher elevation terrain, more susceptible to snow and ice as a result of atmospheric rivers. Next slide, please. For this, we broke atmospheric rivers into 5 categories from 1 to 5, and this is based on work that comes out of my center, our center, the Center for Western Weather and Water Extremes, or CW3E. This is similar to the hurricane scale of 1 to 5 or tornado scale of 1 to 5. In the case of atmospheric rivers, it's a location-specific categorization, and it depends on the duration and the intensity of the atmospheric river. Next slide, please. So this figure shows the impacts of AR1s through AR5s at the 4 different sections of the I-5 in California. As you move to the right, that is a % reduction in vehicle class, in the V-class passenger flow. You can see that by and large, AR4s and 5s have a greater impact. Almost all of these ARs are associated with a reduction in V-class flow. There is an exception here, Central California. For the milder ARs, actually, we saw an increase in flow, and there are a number of possible reasons for that, which I won't go into now. But I will note that the impacts were actually not statistically significant, whereas the positive impacts, the reductions in flow associated with the stronger ARs, those were statistically significant. Next slide, please. So from this, we were able to, from a similar analysis focused on vehicle miles traveled, we were able to estimate the cost of the reduction in traffic flow. So obviously, road travel has value to passengers, to drivers. And so a reduction in travel associated with inclement weather has a cost, an associated cost. And the way we worked out the cost was standard economic theory to calculate the change in the demand associated with these inclement weather events, which you can see on this figure as a shift in that downward sloping curve to the left. So on the x-axis, you have vehicle miles traveled. On the y-axis, you have the price or the value of a vehicle mile traveled. During non-atmospheric river conditions, we estimated 39 million VMT per day. On atmospheric river days, that was reduced by to 38.5 million VMT. And once you figure out the cost of this in terms of reduced what is called consumer surplus, we found that the costs were on the order of $134 million per year. And we did a sensitivity analysis where we varied the sensitivity of demand to the price of travel, and the range that we found was $99 to $295 million per year. But our central estimate was about $130 million per year cost. And this was just for the I-5. We're extending the analysis now to look at the entire California freeway system, but for the I-5 alone, cost of atmospheric rivers was on the order of $130 million per year. Next slide, please. As a final section of the project, we considered the potential value of atmospheric river forecasts to road managers and to drivers. Atmospheric river forecasts have been improving consistently year to year. From 1 to 7 days, we have pretty good forecasts of where the atmospheric river will be and what the intensity will be. And this is because we can watch the atmospheric rivers progress over the Pacific Ocean. And we actually have a program at our center where we fly Hurricane Hunter aircraft that are usually used for hurricane reconnaissance in the fall, in the late summer and fall. We use them in the winter to fly over atmospheric rivers and gather information, which allows us to accurately predict the location and intensity of atmospheric rivers up to 7 days in advance. 7 to 14 days, we can sometimes predict the location and intensity. We can usually predict whether they're going to happen or not, just not exactly where. We also are developing subseasonal to seasonal forecasts for situational awareness, seasonal projections, and using climate models, we're able to look at the long-term decadal projections of atmospheric rivers. So we know that as temperatures increase globally, that allows the atmosphere to hold more water vapor, and that leads to an intensification of most storm systems, including atmospheric rivers. The potential applications of atmospheric river forecasts and improved forecasting technology include road weather management information systems, dynamic traffic signals, maintenance decision support systems, AR warning systems, and long-term infrastructure investments for the climate projections. Next slide, please. So in terms of potential for future work, we are in the process of developing an AR operational product using our latest forecast capabilities at our center, and expanding the AR impact analysis, considering beyond just these 3 test sites, looking more comprehensively at the Western United States. It is possible that ARs have impacts in the Midwest, Southeast, and Northeast. There are ARs in these regions, but in these regions, it's usually other weather systems that cause the greatest impacts on transportation networks. So again, the models that we developed could easily be applied to these other forms of inclement weather systems. We didn't look at freight networks, but this is a possible direction for future work. And we didn't consider the broader economic impacts on local economies. So you could imagine coastal communities where roads are actually shut down along Big Sur, for example, or mountain passes to mountain communities. The impacts could be significantly increased. Next slide, please. I'll actually skip over these next 2. These are just to show the forecast capabilities that we're developing at our center. Next slide. This one, the top center figure shows the error associated with traditional forecasts, and the top right figure shows the reduction in error associated with our new artificial intelligence-based weather forecasting systems. So you can see that, well, it's not obvious from these figures, but maybe take my word for it. There are significant improvements in the forecasts associated with incorporating machine learning and artificial intelligence techniques into the forecasting methods. Next slide. The goal here is to be able to develop a tool that can be used by road managers and that can be presented to drivers to alert them to changing weather conditions. Here we see a color-coded system for I-5 showing where impacts are likely to be greatest. Next slide. This could be presented in terms of the increase in accidents, for example. Next slide. Or economic impacts. One more slide, please. So to summarize, we found that atmospheric rivers decrease traffic flow, increase accident costs, and increase delays. And these changes in the road transportation network system, these impacts can have significant costs. One more. I guess two more. Potential future work I mentioned, so expand the analysis, consider freight impacts and broader economic impacts. And next slide. I'd like to thank a number of folks at different state departments of transportation who reviewed our work, and also folks at the Aurora program for sponsoring this work. Thank you.
All right. Thank you, Tom. Next up, we'll be talking with, or we'll have Eric Schoening on from the National Weather Service to present. And I think what Tom presented there segues nicely into kind of the National Weather Service side of things and how they help get the California partners prepared for these types of events. So real quick, Eric Schoening is an emergency response specialist, meteorologist for the National Weather Service. He works with a wide variety of state and federal level partners across the Western U.S. He is also the Surface Transportation Program lead for the National Weather Service Western region. Eric, I'll pass the mic to you.
All right. Thank you very much for that introduction. I appreciate it. Good talking to you all today. As was mentioned, I'm a meteorologist with the National Weather Service. I've been with the Weather Service for about 18 years now, which is hard to believe. And for the past 7, I've been in this emergency response specialist role, working with a wide variety of people across the West. Hopefully not too intimidated by the title of my presentation today, National Weather Service support of California wildfire operations before, during, and after the fire. If you're not in California, probably about 90% of what I'm presenting will be applicable to you outside of California. And if you're not too involved in wildfire operations, I think about 90% of what I'll say is also applicable to a wide variety of hazards that the Weather Service forecasts and supports partners with. I also know that this is transportation focused, so I will also weave in some transportation impacts as well. On that note, please, next slide. So just a quick Weather Service 101. I imagine a lot of you are familiar with this, but just in case you're not, really the backbone of the National Weather Service is our weather forecast offices. We have 122 of them across the United States. When it comes to the state of California, there are 10 offices that serve the state of California. And you can see here an overlap of the National Weather Service offices with the Caltrans districts. So as you can see, it's a little complicated to get that coordination right. You know, each Weather Service office has multiple districts to coordinate with. And in some cases, you know, districts have multiple forecast offices to coordinate with. So that's really a partnership that's been built quite a while over the years. You know, obviously, support from the Weather Service to DOTs varies quite a bit state by state, depending on the size of your state and how your transportation is organized. You know, some of it's at the state level. Obviously, quite a bit of work with the Pathfinder program, among others. But with Caltrans, really a lot of, if you'll excuse the pun, where the rubber meets the road is with these districts. You know, a lot of the work is done at the district level, and that's where a lot of our coordination happens, is between the districts and our local offices. Next slide, please. So first I want to highlight on what we do before a wildfire even starts. And the first one there is building partnerships. I could probably do a whole presentation on building partnerships alone, because it's really one of the most important things, if not the most important thing, that the Weather Service does. You know, during blue sky days, we take a lot of time to get to know our partners, to really understand their needs and what, you know, they really need as far as weather details, what their, pressure points are, that sort of thing. So I listed here, you know, among our California transportation and wildfire partners, Caltrans, Cal OES Fire, Cal Fire. And really that's just scratching the surface of our local, county, state level partners across the state and really across the entire country. So that's really something that we really put a big focus on, is making sure we know our partners before an event happens. We do a lot of coordination with our fellow meteorologists. There are a lot of meteorologists outside the Weather Service in both the private and public sector. when it comes to transportation, a lot of states, and I believe some of the Caltrans districts have contracted with private weather vendors to get more detail than the Weather Service really can provide. So we coordinate with them to make sure that we have a collaborated message, make sure that you're not hearing two different things from two different people. So we get the big message out to both our partners and the public. And then those private companies do a great job of really getting those details that the DOTs care about, including things like maintenance crews and plows, and getting specified forecasts for those. In the private sector, we also coordinate with the utility companies, especially when it comes to things like power safety, public safety power shutoffs, or PSPS. That's a important and growing concern across really many states, but especially in California. So we coordinate with those private sector meteorologists as well. And then when it comes to wildfires, one of our biggest collaborators is the Geographic Area Coordination Centers, or GACs. They have some meteorologists there as well that really take a close eye on things like fuels when it comes to wildfires, and really helps us collaborate our message when it comes to what conditions are going to make explosive growth for wildfires. We do a lot of work with crews doing prescribed burns. So when it comes to managing things like forests and making sure some of these fires can't get out of control ahead of time, we do a lot of work with them. That includes planning forecasts. So if they know they need snow cover on the ground or that sort of thing, they'll call and talk to us about what conditions they need to burn. And then spot forecasts are really a big deal as far as getting the conditions right to make sure that's done safely each time. And then once we get closer to an event, obviously, big part of our job is communicating the forecast. Even before we get to the day 1 through 7 period, a lot of our longer term outlooks are getting more and more skillful, especially in that 8 to 14 day period. We can really start to see some of these big events coming before they start, and we try to message those as best we can. And then when we do get within 7 days, we communicate in a wide variety of ways. You've probably read some of our forecast discussions. We send emails to partners. If you're not on your local weather services partner email list, it can be quite helpful in identifying these events, whether they're going to be big or small. As things get closer, we'll often do webinars. And of course, our bread and butter are traditional watches, warning advisories, with red flag warnings being really the big thing as far as fire weather is concerned. Next slide, please. So during the wildfire, one of the first things you have to do is find out where the wildfire is. So we do a lot of hotspot detection via satellite. Our latest generation of satellites can see those hot temperatures when a fire gets big enough or hot enough. So a lot of our offices have programs in place to identify where new wildfires pop up and notify the officials. And oftentimes, or at least in many occasions, they're able to identify where those fires are before it's even seen on the ground. So that's something that's really helped with identifying those fires ahead of time and getting the firefighting crews there sooner rather than later. Obviously, once the crews are on the ground, spot forecasts are a really big deal again to get them the weather that they need. And good old-fashioned phone calls really are a big deal as far as just talking about what you care about and what you're concerned about when it comes to the fire. That said, we can provide the weather, but it's really the fire experts, including the fire behavior analysts, that know how the fire is going to spread. So if you call the weather service, and ask, is this fire going to cross the interstate? We'll be able to give you the winds, but really it's going to be the fire experts who are going to know exactly how that's going to spread and how quickly. And of course, during this period, we continue to collaborate with those private sector meteorologists at the DOTs and other organizations. And then when things get big enough, we do on-site deployments of meteorologists. Many of you in the fire community may be familiar with our incident meteorologists, or IMETs. They deploy to wildfires quite frequently across the entire country and support the crews on the ground there. But they're also trained to deploy to other incidents, such as hazmat, for example. So obviously a great resource there. We also deploy meteorologists to city, county, and state EOCs. That picture there on the right is myself at the California State Operations Center, I believe during the Palisades fire. So we've really put an emphasis on that recently of deploying meteorologists to these locations, talking eye to eye with partners. And I put on here, we've even had some deployments to traffic operations centers in a few places. So if that's something that you've never thought of, but you're thinking about it, like, we could use a meteorologist either, on a scheduled basis or during big events at one of our traffic operations centers. Think about it. Maybe talk to your local National Weather Service and see if that might be a possibility there. Next slide, please. And after the wildfire, surprisingly, this is actually the most words on any of the slides because there's still quite a bit of work to do after the wildfire. At the top is kind of a continuation of what we were talking about before with spot forecasts, with on-site deployments, with verbal briefings. Really, a lot of that continues after the wildfire during cleanup because there's still obviously quite a bit to do there on the ground. We can also provide targeted email support for those recovery operations. You can see one example there in the upper right. I believe that's from the Sacramento office. But those can really be tailored for your needs and your thresholds, no matter what it is, whether it's recovering from a wildfire or if you have an extended period of time, like rebuilding a road segment. That's happened along the Pacific Coast Highway in California. If you have crews on the ground for an extended period of time during recovery and cleanup operations, it's really important to know where those safety thresholds are as far as weather concerns go. So we're happy to support that, even if it's going to be weeks or months of work there on the road. Obviously, after fires, debris flows are a big deal. We work with the BEAR teams, which are built up with numerous experts, many organizations on these teams to find out what the thresholds are for these burn scars and really kind of look at the impacts. Will this impact roadways? And if so, will it also need evacuations? I've seen that in multiple occasions where, those after the fire is just as impactful, if not more impactful, because it can close roadways, it can impact houses yet again. So you can see an example of a debris flow there, actually from Utah back in 2014. They're crossing a roadway on the bottom right. From the Weather Service, we can, again, provide specific email briefings tailored to those thresholds, tailored to those rain amounts and rain rates, and really let you know when the periods of most concern are for those debris flows. And so you can stage crews ahead of time or close roads ahead of time, depending on what the situation is. Next slide, please. So really, that's all I had. I just wanted to give you a quick overview of what we do. Thank you very much for listening. If you have any questions, please feel free to reach out to me or anyone on my team here at the Western Region Regional Operations Center. Thank you so much, and have a great rest of your day.
All right. Thank you, Eric. And it's a pleasure as always to have you on to talk about weather with you. So we'll move on next to our last presenter, Robert Scott, to round things out with the fire service and their response to some recent events. So Robert Scott is the Assistant Chief at the California Governor's Office of Emergency Services, Fire and Rescue, and the Fire Risk Program Coordinator. He brings extensive experience from his 30-year career in emergency management, having held various firefighting, land management, and leadership roles. He's an expert in fire behavior analysis and intelligence, having contributed to major incident management teams and now overseeing real-time intelligence for California's emergency management organization. Robert, I will pass things over to you.
Thank you, Jeremy. Can you hear me?
Yes, perfect.
Fantastic. Yeah, and thank you, Jeremy and Kayla, for inviting me today. I just wanted to open by clarifying what it is that Cal OES Fire and Rescue does. We are a support agency to frontline response organizations in California and both nationally and internationally. So we don't necessarily put the fires out, but we provide equipment and manpower to help the agency having jurisdictions at the events do that work. And so we're here today to talk about Fire Integrated Real-Time Intelligence System. Next slide, please. So fire integrated real-time intelligence system is an idea that you can leverage modern technology and aircraft to gather intelligence about things that are happening in the environment. Now, we were born out of fire, but we're doing more than that now. One of the reasons I think I was invited here was to talk about some of the stuff we're doing in public emergency management, specifically with infrastructure. So next slide. A little bit about the FIRES platform. The FIRES platform is a 24-hour-a-day, 7-day-a-week operational program. We fly 2 aircraft, one in Chino, Southern California, and one out of McAllen near Sacramento. And we have 2 shifts a day from 8 in the morning till 2000 at night. And each one of those shifts has a mission commander, a qualified airborne sensor operator that manages the sensing capability of the aircraft, and a pilot in command. And again, that's 24 hours a day, 7 days a week, 365 days a year. Additionally, the vector the aircraft to places where it needs to be. And we also have a modeling wing, and we'll talk about that more in a minute. Next slide, please. So a little bit about the aircraft. These are King Air B200 aircraft. They are equipped with a suite of sensors. Starting from the top going down, there's a KA-18 satellite uplink. It's capable of about 20 megabits, so about 720p HD live stream capability. We can't do both things at once, so if we're trying to download data out the aircraft, we have to turn off the live stream and let that data flow from the aircraft out to our customers. We have a FLIR 380 HDC sensor. We have a TK8 sensor now that we just upgraded. We'll talk about these sensors in length shortly. We have a Terrain Mapper 2 LiDAR system. And we also have a NPS 7, which is a synthetic aperture radar. And then finally, on the bottom of the aircraft, we have an MPU 5, just kind of a warfighter type mesh network system. If you have firefighters on the ground or responders on the ground with an ATAC or tablet command type system, the information from the aircraft can flow directly to the ground, not having to make the jump up into space and then back down ground-based or cellular type connections. Next slide, please. Glamour shot of the airplane there at McClellan. And the slide on the right is the interior of the aircraft. What you're looking at there is the ASO station. There's several computers and equipment that make it all run. One of the major limitations of the aircraft and the program is that we're right on the edge of the amount of power that the aircraft is able to generate in order to run all these sensors. So we have to ask before we go fly, what is it you want us to do, so that we can prepare the aircraft with the proper sensors, or at least make it known that we can't do everything all at the same time. We have to make a decision about what we're going to do. If you look to the front, you can see the pilot station there. The pilot flies on the left, and then the mission commander will fly on the right to help with cockpit resource management. And then they'll move to the back of the aircraft during collection to help the ASO better understand what the target is and what the objective of the collect is. So next slide. So if anybody has ever heard of the FIRES program before, this is where I give a shout out to Chief Brian Fennessy from Orange County Fire Authority that had the vision to find the funding and the people to build a program that took a basic sensor package, a 380 and a TK sensor, and some cellular connectivity, and go out and find fires in the wildland. So there was a plane, there was a way to collect data from the environment. So again, think back to cameras. Originally, this program was in Southern California only. So they were listening to the dispatch centers when there was a wildfire. They would launch the plane, and it is basically where's the fire, how big's the fire, where's the fire going. And again, on the right-hand side there, you see a little bit of the fire modeling aspect of what we do. We'll talk about that on the next slide. So a standard product set from Fires in the Wildland arena is a model. That picture on the left is a wildland fire model. We use Farsight. We use static weather. We are working on bringing that into more of a probabilistic type model. More to follow on that. You have a picture in the middle. That is a infrared representation of the fire, where it's hot and where it's not, basically a perimeter. And then on the left is a slide from either a full motion video or a picture of what's happening. You can see that is the Palisades fire moving towards the west, coming down off the hill into some structures or some values at risk. Next slide, please. And then additionally, we can push out more graphical representations of the fire. The picture on the right is just a snapshot of, or a screen grab from a common operating picture. It gives you a little bit better idea about where the fire is in terms of the structures. And then that on the left is a screen capture, and I believe that was the Palisades fire, again, at nighttime. But for a fire commander or a fire manager or responder on the ground, that's valuable information that lets them understand what the possible impacts of the fire are and where to best deploy their resources. All right, next slide. So some of our successes, we create unique partnerships, specifically California Highway Patrol, Civil Air Patrol, California Department of Transportation, and Geologic Survey. And we help out trying to understand how avalanches, earthquakes, and the movement of earth impact what we do in the state of California. We stood up a blob storage solution that transition our access to data to our partners in a more secure and robust way. These sensor packages generate massive amounts of data, and we're just not to the place anymore where we can pass thumb drives around or just take pictures. We'll talk more about some of the data that we generate. We provide real-time customer support. In the event that your agency needs something from the fires program and can't readily interface with our distribution systems, our Fusion Center will work with you to get the data where it needs to be so that you can utilize it in a advantageous fashion. We maintain a 95.6% uptime. Basically, that means that the aircraft, except for periods when there is mandatory maintenance, we are available 23 out of 24 hours a day, which I think is pretty good because, you know, a plane is not a car. You have to maintain it. And when it doesn't want to work, you can't just go out and fly it. So we are very proud of our subcontractor, Dynamic Aviation and Avix Aerospace, for providing the aircraft at that level of readiness. And we're, let's see, aviation program availability during high impact weather events. We strive to have the aircraft available to fly. Unfortunately, during the events of January 7th in Southern California, historical levels of wind, our aircraft was grounded at the Chino Airport, which means we had to vector the northern aircraft down, which was an additional about 4 hours of flight time. But we were able to get down there and do that. We have since made changes in the program to address that so that we can have a higher uptime during impactful periods. Next slide, please. So in terms of training efforts, we maintain an annual training program that ensures flight crews can conduct safe flight operations and aerial sensor correct proficiency. We participate in the joint all hazards assessment and awareness exercise with our partners at Department of Defense. We practice what we will do in the event of an impactful event. So earthquake, flooding, biological release, or improvised nuclear type detonation. How are we going to go out and provide information back into the State Operations Center or headquarters here at Cal OAS, and then again out to the responders on the ground so they can make good decisions. And we're also beginning an effort to create mission profile standardization so the customers and the public understand what our capability is. And when you ask for a flood inundation product, you understand what you're going to get at the end. You can be prepared for that data when we provide it to you, and everybody's on the same page about what the capabilities of the program are. Next slide, please. So really quickly, the four things that we do the most, obviously, are wildland fire. We do training. We maintain a training regiment Airplanes don't like to sit, so we like to get out and fly them about every 48 hours. We participated in a lot of search and rescue with our partners here at Cal OES on the law side of the branch. And then that other is some of the flight time that's increasing, sensor testing, general aviation requirements, and new and exciting ways to leverage the sensor packages. So next slide. So those are data collection. Aerial data can be requested by the customer and can require additional post-processing. So mud and debris flow, landslides, damage assessments, infrastructure inspection. And we also can do reconnaissance, no notice aerial collections of assets or of potential impacts that could be benefit from fire support. So we can go out and take pictures or full motion video of earthquakes, hazardous materials, hurricanes, landslides, avalanches is another one we do. Swift water, we've been involved with that. Maritime hurricane, we had Hurricane Hillary, I don't know, 18 months ago, I think, that impacted Southern California. We flew we flew beach erosion missions to get a better idea about how the beaches fared during that event. Next slide. So our flight hours, we flew in 2023, 824 hours of flight time. In 2023, that represented about a little less than 50% of all the IAA hours flown in the country in wildland fire, and not counting anything that FEMA is doing, but generally in the emergency management and wildfire world. And you can see a major slice of that is wildfire, with about 20% being training and the rest being data collection and search and rescue. Next slide. 2024 saw about a 20% increase, so 1,000 flight hours. 2024 was a very large wildland fire year. We counted everything that we did in support or a second or third order fire effect to be a wildfire collect. So there's some data collection we did for mud and debris flow. We'll talk about that shortly. Or impacts to roads, that gets counted in there. But you can see, obviously, our training hours went down quite a bit because you don't need to train as much when you're always going out and flying. Data collection, search and rescue remained about the same. So next slide. So you can see that there was a major increase in 2024. Another part of that was that during 2024, there was major fire impacts both in U.S. Forest Service Region 6, which is Oregon and Washington, and U.S. Forest Service Region 3, which is Arizona and New Mexico. Their fire load significantly reduced the available IAA capability in California, and FIRUS stepped into that role to provide support while other IAA assets were brought online by our partners, both at U.S. Forest Service and our state partner, CAL FIRE. All right, let's talk about sensors. Next slide, please. So sensors and data acquisition. The primary sensor that you would see a picture of if you are watching the news or see general data from the program is the Starfire FLIR 380 HDC. So this is a standard ball mount sensor. It senses in infrared and electro-optical. It has laser range finding capability. It has target tracking capability. And it's basically just a fancy camera on the bottom of the plane that can auto track, and it gives pictures and range information about targets in the environment. Next slide. So here's some data collection. Next slide. So February 18th, 2025, there was a train derailment. The Tehachapi Circle, I think this is, coming from Bakersfield, headed up into kind of Lancaster, the high desert east of the LA basin. Train had derailed. There was some concern that there could be some impacts from hazardous materials on the in the train cars. And so we flew this mission in support of our partners at National Transportation and Hazmat. These pictures are taken from about 10,000 feet and an off angle of 45 degrees, so a good 15,000 feet away maybe. And if they really zoomed in, you could probably see people. It's a little bit too far to see the placards on there, but if you needed that, we could get a little bit closer. Next slide. And that right there is about the limit of what we can do at 11,000 feet. And we usually fly 10,000 feet above the target. And so that target, yeah, is 4,300 meters away, about 2.7 miles. You might be able to get a little tighter than that. But again, if you needed to see the placard, you could do that. You could definitely see responders on the ground. I see 2 people standing there next to a dozer and some trucks. It's pretty amazing what these sensors are capable of. Next slide, please. April 25th, 2024, Orange County Pier Fire. The fires program was made aware of a commercial fire at the end of the pier in Orange County. The fusion center managers vectored the aircraft to the incident, and we were able to provide real-time intelligence to the firefighters that were pinging this fire or suppressing this fire. This is at the end of a very long pier. I want to say it's like 1,000 feet long, maybe a quarter mile. So it was a long hose lay out there. In the picture on the right, you can see the helicopter dropping. That's a shortwave infrared picture. And you can definitely see the heat coming off of the incident. Next slide, please. And so in this picture here, you get a better understanding of what is on fire, what's not. Picture on the right, you can see the reflection of the infrared energy coming off of the water. That's more of a long range infrared picture there. But moving back to the left, you can see the fireboat. The fire commanders were able to determine that the integrity of the pier just to the inland side of that building was safe, and they were able to extend a hose lay out to that in support of the ocean-based fire apparatus. Next slide. This was the LA County Seaside incident. This was a semi-truck that was moving a prefabricated battery boosting type machine. I'm still a little unaware, or I still don't quite understand what it was, but I think it was something that you would put like where a battery charging, you know, like a battery bank would go, and you would put the main power into it, and it would store that energy. So during high peak loads of lots of cars charging at the same time, this would provide supplemental power. So this vehicle rolled over. It looks rather benign. However, if you go to the next slide, you can see that it's really hot in there. They moved the aircraft around. They got a better shot down low at the piece of equipment. Again, the long wave infrared, it's kind of blown out. Long wave doesn't do a good job of really pinpointing it. However, the picture in the upper right was able to be utilized by the incident commander along with the manufacturer of the device, and they could tell exactly which battery is on fire and what that meant in terms of suppression and how long it was going to take to mitigate that hazard. Next slide. So the next sensor we have that we use, one of the largest amounts of data that we create is our Overwatch TK8 sensor. This is a sensor that scans back and forth across the landscape. We get about 70 degrees of a scan each time it goes back and forth, and it's a multispectral scanner. It scans in shortwave, midwave, long wave infrared, RGB, near infrared, and any mixture of those two things. So it can take pictures, but it can also do mapping, and it is the primary mapping for wildland fire that we do. Overwatch and AVEX Aviation provides a proprietary piece of software that looks at the infrared composite images and generates the fire perimeters that we saw earlier, but does lots of other things too, and we'll explore that now. Next 2 slides, please. So the Arroyo Seco, a little bit of area orientation. This area is south of San Francisco, and more specifically, it's just south of Carmel Valley in Monterey County on the central coast of California. So next slide. This is a Google Earth image of the landslide. That is a kind of a decomposed granite, a loomy kind of soil that's sliding down into the Arroyo Seco River right there. And there's a major thoroughfare, a road right there that you can see that needs to remain open. And our partners at California Geologic Survey and Caltrans are very concerned about the movement of that landslide, so much so that they used to send survey crews out every year, or I've heard varying reports, but every once in a while they'd go out and they'd have to survey it to see how it was moving. They asked us if we could fly the TK sensor in support of digital elevation models, and we obliged. Next slide. This is a representation of what that data looks like. It's just picture. It is a picture. However, we fly high overlap strips, meaning that each individual spot on the landscape is photographed from 8 different strips. And you can do some math and you end up with a 3D elevation model. Next slide. So California Geologic Survey took that data and they generated this model here. And this is super cerebral, so I always have to look at it to make sure I'm talking about it right. This is the the horizontal movement. So flat across the ground. You can see that the slide is moving to the south in this representation here. That's a great picture. Yes, it is moving, but more importantly, how is it moving vertically? Next slide. And here is a representation of the movement of the slide vertically. You can see the red, it's sinking. Obviously, there is a fissure opening up at the top of the slide. The graph that you see on the left there is a representation of the line kind of moving from the northwest to the southeast. A little dyslexia there. I gotta get it straight in my head. But you can very plainly see that there is a large vertical movement, and I believe that vertical movement is 2.5 meters down at the bottom. So that ground is sinking. Interestingly, down in the Arroyo Seco drainage right there in the bottom left of the picture, you can see large chunks of material that have fallen into the river, and that you can see the scouring around it from the last water event. So amazing resolution. These digital elevation models are good down to about 10 centimeters. So not quite survey quality, but definitely enough quality to tell that you've got a large amount of material that's moving. And if that ends up on the road, we can get a better understanding of how much and how long it's going to take to move it. Next slide. We also can do digital elevation models of mud and debris flow. Next slide. So this is a product that we generate in support of California Geologic Survey. And again, there's a long connection between this and what my colleague Eric does. We were asked to go out and collect digital elevation models through TK sensing of a fire. I believe it was the Butler fire, kind of outside of Lancaster there. U.S. California Geologic Survey then took that data and created models about what the current state of the landscape was, and then USGS combined that with highly accurate what kind of soil is there, and they created an output that talked about the risk of a debris flow for a given amount of rain. Okay, so we're almost there, bear with me. And so then if you take a model like a GFS rainfall amount model, and you say that there is going to be 20 millimeters of rain in a 1 hour period, then you can get a risk model that talks about the probability. You can get a probability model that talks about the chances of a landslide happening or a mud flow happening. These are highly accurate maps. We as OES don't talk about what the risk of the mud flow is or what the probability of rainfall is. However, we do assist the agencies when they ask for help based on data that is generated from these products. Next slide. And so sadly, one of the other things that we do is we can do rapid damage assessment. These are examples from the LA fires, Palisades and Eaton. Next slide, please. And so I have to open this statement by saying it's not the job of Cal OES Fire and Rescue or the Fires Program to talk about what the impacts are. That is up to the agency having jurisdiction. We provide data, sometimes information that somebody else can turn into intelligence. However, it makes sense for OES to have an understanding about what the impacts are, because this piece of data information suggests that there were 5,204 structures that were impacted by wildland fire, and that's 20,000 people that in the next 48 hours are going to need shelter and support. And it is advantageous for an emergency management or support agency to understand what the impacts are and to rapidly provide that assistance. So now that I've said that, we'll get on to how we generate these products. At the end of our collect cycle, we will fly one more time over the top of the fire, creating a quick mosaic of blended infrared products that kind of give an idea about where things are hot on the landscape. Our analytics team at UC San Diego will then compare that to building footprint data. And if there's concurrency between a hot spot on the ground and where a structure, where the building layer says a structure is, we will count that as a structure that has been impacted. These are by no means accurate numbers. However, we have found success. We're usually within about 10% of what the final number is. So again, we're not trying to jump ahead or speak for the agency having jurisdiction. We're just trying to get a better understanding about what the impacts are so we can provide support to the citizens of California. Next slide. A similar effort here on the Eaton fire. The Eaton fire was about 20 miles to the east of the Palisades fire. It started the night of the 7th as opposed to the early morning or the late morning of the 7th of the Palisades fire. And again, we were able to overfly the incident. The green outline is the fire perimeter. However, we flew back over with the sensor tuned specifically to gather multispectral IR images, infrared images, and to generate this product. And this one said it was 6820 total structures affected, and I think those numbers are pretty close to what the DINS teams on the ground were able to collect. All right, next slide. So how are we evolving? So the fires program, while we do wildland fire and some of these other aspects, we are evolving. We are experimental in nature. We look for new and unique R&D applications of existing technology. And we have two new pieces of equipment that we're using, LiDAR and synthetic aperture radar. Next slide. So we recently acquired through our contractor a Leica Terrain Mapper 2 LiDAR sensor. This creates highly accurate three-dimensional depictions or models of the landscape, accurate down to centimeters, millimeters maybe. This is a really hard sensor to use and to get to work at that level of accuracy, but we continue to try and do that. Some examples of what we've done. Next slide, please. This is the Indian Valley landslide. This is just a little bit east of Clear Lake, kind of north of Sacramento a little bit if you're thinking California statewide. There is a area of land that is poised to slide down into this Indian Valley River creek. And if it does that, it will create a dam. Next slide, please. And you can see on the left-hand side of the picture, kind of actually dead center, you can see the slide kind of coming out of that east aspect right there. And down past the river and down in that valley down there is a town, and I forget the name of it, I apologize. But this was the original use case of our TK sensor. We had collected on this several times, and that was great data. And now we're trying to do LiDAR to see if we can get even better data. Again, once that slide slides into that river drainage, it will create a dam, and that dam, when it eventually erodes that earthen blockage, it will create a increased water flow down there. That would be not good. We don't want that. So this image is our three-dimensional model overlaid on a Google Earth picture, satellite picture. The sensor does have the capability to take pictures, or we could provide our own TK images over the top of it. That's a work in progress. That's not in our product set right now. We're still just trying to figure out how to take good LiDAR data and provide support to our partners with that. Next slide, please. And finally, the synthetic aperture radar. This is an MPS 7. This is kind of a military grade type sensor. It'll do moving target. It will do target designation. It's my understanding that if you put a Coke can on a freeway and then you fly 100 nautical miles down and come 100 nautical miles back and remove it, the sensor knows it's not there anymore. It doesn't know what it was, but it just knows something was there and now it's not. So this has great applications if you're looking for somebody, say, in the snow, or you're trying to determine how something that is static has changed. Next slide, please. So the use case for this was 2023, I think, when I first started here. The Pajaro River, just south and west of Salinas, California, had ruptured a levee in that area. And this is a community of approximately 5,000 people. We were requested to try and determine, the fires program was requested to try and determine how deep the floodwaters were. We flew the synthetic aperture radar in support of that effort. We gathered data. You can see that raw data on the left right there. We compared that with a publicly available Google digital elevation, Earth elevation model. We did math, and we found that the floodwaters were approximately 2 feet deep. You can see in the picture in the middle there, which was San Jose Mercury News from one of their helicopters, that there is substantial inundation around those buildings or structures. Turns out synthetic aperture radar is not good at highly cluttered and reflective environments. There are some filtering things that we can do to try and improve that. However, outside of the urban area, you can see that it was relatively accurate. If you zoom in on that picture in the middle, you can see that the water is about 2 feet deep. It's up about the middle of the grills on the vehicles. Those vehicles probably aren't totaled. The reason this is important is because, generally speaking, if a structure is not impacted above the light sockets in the building, you can just take the carpet out, cut the bottom of the drywall off, and the structure is inhabitable, right? After a little bit of work. However, if the water is above the light sockets, you have to tear out all the drywall. There's subfloor issues. Those individuals are going to need long-term assistance. And so if you've got 500 houses that have more than 18 inches of water in them, that's 2,000 people that you have to find housing and support for. Again, a great tool for OAS or our partners to understand what impacts are. All right, next slide. So a little bit of pitch about what OAS can offer. We have a common operating picture, or a COP, that is, if you are in emergency management or basically anybody in public service, you can scan that QR code right there and sign up for the Next Gen Scout tool. This would be a great place for you to find the FIRUS data. Anybody that's familiar with the Forest Service's EGP tool, they are brother and sister. Ours isn't quite as capable as EGP. However, the Forest Service has transitioned away. They now use Next Gen EGP, which is more of a ArcGIS online type product. And this is what we're using now, and you're more than welcome to sign up and utilize it. Next slide. If you want FIRUS data in real time, we use the Slack application. The Slack application was originally designed as a coding and programming platform for teams to work together. The OES needed a secure and archival type system in order to disseminate the data. This was the contract that we went with. It's not perfect, but it definitely gets it done. If you want the real-time products that the FIRUS program generates, this is the place to go. You can scan that QR code right there, and you can sign up. They're both Microsoft Sheets. The team with the FIRUS program will get you signed up for both of those applications. Next slide. Well, that's it. FIRUS integrated real-time system. One question that I get a lot is, how do you order it? We are a no cost to the end user program. We will entertain and attempt to do everything we can to help you. And if you would like to request it and you don't know how, you call the FIRUS duty line right there, and you'll end up talking to myself or one of the other assistant chiefs in Cal OAS, Fire and Rescue, and they will help you better understand what we can do to help you. If there aren't any questions, I'll throw it back to Jeremy. Thank you, everybody.
It looks like we actually do have 2 questions in the chat there.
Cool.
while we go through, and I'll ask these real quick and we can answer them live, but while Robert is answering these questions, if anyone else has any questions, please use the Q&A real quick so that we can get those in front of Robert too. So anyways, first question for Robert here from Mary Angelica Deeb. For the virus presentation, the data and images you collect could allow you to run different cases or scenarios that help you learn about fire conditions and events. Do you share that with others? And are there other teams you collaborate with to learn, national or international? I think you already answered that, but
Yeah, it's the policy of OAS to provide that data to academia. However, if we get a lot of questions right now for training AI, and the policy is that if it's for commercial use, we would have to enter into a MOU in order to do that. We're not quite there yet, but we do share our data with UC San Diego, the UC system in the state of California, and our data is ingested into other common air operating pictures, including Cal Fire's research and R&D program, and the U.S. Forest Service uses our data too. However, if our data is freely available on National Interagency Fire Center website, so if you have any access to fire data in general, you can get the data that the fires program generates.
great. And then the second question is from Lyle Unwin. It says, "Hi Tom, are the disruption costs from your studies borne by the user only, or do they include owner costs as well? Thank you."
The work that the fires program does is at no cost to the end user, and so we will, if there is a use case or an experimental thing that we can do with the platform that will add to the suppression, or I'm sorry, the response capability, we will entertain it, and most often we will do it. So we fly a lot for Caltrans during snow impacts. We fly a lot for California Geologic Survey, creating digital elevation models. And we've begun to fly quite a bit for emergency management organizations in support of rail cars on fire, flood impacts to roads. We will, if it's an emergency and you need data, we will help you collect that data. No cost to the end user.
Yeah, thanks. I believe that question actually, I misread it as I was queuing it up, but that question came in a little bit late, but it was for Tom.
Mm-hmm.
Tom, did you want to take a stab at that from UCSD?
Sure, yeah, it might have been for Robert, but I can just say that for our studies, the cost estimates that we derive were for for passenger vehicles only, and for the drivers and their passengers.
Got it. Thank you, Tom.
That's definitely in Tom's lane.
I think you both handled it very well. And looks like we don't have any more questions in the chat, so I'll head towards wrapping us up. If anything else does drop in, we'll go ahead and circle back to it. So let's see. Kyla, do you want to pull up our last slide? There you go. So I don't have an official slide for it yet, but as you know, this Spotlight series is we try and put out some new content every 2 months. The next webinar like this will be in September, and the topic that we're planning to cover is the science behind snow fencing, and then also starting and managing a snow fence program at your state or DOT. These topics will change as seasons change. Obviously, people are starting to ramp up their efforts for winter operations. So by the time September rolls around, I know many of you will start, you're already training drivers by that point. And I think that this is a pretty good topic to cover. As always, I appreciate everyone for showing up. If you do have any future topics that you want covered in this webinar series on road weather, feel free to reach out to me at the contact information there on your screen. Or if you just have anything road weather related that you want to talk about, I'm definitely open to it. I do want to thank our presenters, and I want to thank NOCoE as well. I think without any of them, this wouldn't have been such an informative presentation today, as well as the rest of the Spotlight series webinars. It's with their help and support that we're able to keep this series running. So I want to thank them, and I also want to thank you guys for showing up and paying attention today. This is some pretty cool stuff that we covered, and kind of outside of the normal things that we cover. So I like to do these these interesting topics. If you're interested in keeping up to date on the other road weather management stuff we have going on outside of the Spotlight series, go ahead and you can register there at the Gov delivery link there in the middle, and that will, and I think it's posted in the chat. That will get you access to, anything that we put out periodically, whether it's publications, newsletters, events, and then you can also register there at the link at the bottom to access any updates from NOCoE themselves. Kyla, is there anything else that you would like to add?
Not too much. Just want to say thanks again to all of our presenters. Thanks for attending today's webinar. Thanks, Jeremy, for moderating. I think it was a really interesting presentations and conversation today. So thanks so much. And as I mentioned earlier, the recording will be available on the NOCoE website pretty soon. So again, that's transportationops.org. But otherwise, thanks everyone, and hope everyone has a great day.
All right. Thanks, everyone. See ya.
Thank you.